Hello students, in this lecture video let us discuss two phenomena. One is Coulomb blockade, the other one is single electron transistor. First let us see what is Coulomb blockade. The resistance offered by electronic structure like quantum dot for further electron transport due to Coulombic repulsion forces is called as Coulomb blockade. Let's see one by one. So we'll take an electronic structure like quantum dot, and suppose if electrons are there in the quantum dot, it will not allow further electron to occupy the quantum dot because electron inside the quantum dot will repel. This repulsion you call it as the Coulombic repulsion. So the Coulombic repulsion in a quantum structure like quantum dot for further movement of electrons is called as Coulomb blockade. That is the resistance to the electron transport by the electrostatic Coulombic forces in an electronic structures like quantum dot is called as the Coulomb blockade. Right? So Coulombic repulsive forces we already know, and two similar charges will repel each other. So electron in the quantum dot will repel further electron movement inside the quantum dot. This you call it as the Coulombic repulsion, and this repulsion will prevent further electron transport and in the quantum structure, and this you call it as the Coulomb blockade. Right? So you know what is meant by quantum dot. In our previous lecture we have discussed what is quantum dot. In the last column in the screen you see quantum dot. Quantum dot is a zero dimensional structure. All the dimensions are in nanometer. It is confined in all possible three directions. That is, the charges are confined. Say for example electronic charges like electrons are trapped inside the zero dimensional structures. It cannot move in any one possible direction. All the three directions the charge movement is confined. This you call it as the quantum dot, which we have discussed in the previous lecture itself. So coming back to Coulomb blockade. So here you have the picture may be slightly invisible, right? Here you have a quantum dot. Here you have a quantum dot. Here you have a source, and this side similar to the source you have a drain. Right? So three terminal device. So source, a dot, quantum dot, and a drain. The source and the dot is separated by a thin insulating layer. Similarly, the quantum dot and the drain is also separated by a thin insulating layer. So if at all an electron wants to transfer from the source to the dot, it has to tunnel through the insulating barrier. No other option. Right? So this arrangement. In this arrangement, the quantum dot, if this quantum dot is having a negative charge, say electrons inside it, it will not allow further electron to tunnel from the source to the quantum dot, as it will repel. This you call it as the Coulomb blockade. So a quantum dot has a capacitance, say C dot. Why we associate a capacitance with the quantum dot? Any structure which stores charge has a capacitance. The quantum dot also stores electronic charges, say electrons, therefore it behaves as a capacitance with a capacitance value, say C dot. Now if I want to add one more electron to the quantum dot, then negative charge electron, say one more electron to the quantum dot, then I have to supply a charging energy EC, which is given by this formula. So EC is equal to E square by 2C dot. So E is the charge of an electron, and C dot is the capacitance of the quantum dot. See here, as the capacitance of the quantum dot is, the quantum structure is very less. Quantum dot is a zero dimensional structure, and the capacitance will be very less. As a result, EC will be more. So as the structure gets reduced, this energy to transfer an electron increases. Therefore, it is very difficult to transfer an energy from the source to the quantum dot because of this small value of the capacitance. Right? Now coming back to the Coulomb blockade, the condition for the Coulomb blockade should be such that this EC should be much greater than the KBT. KBT is the thermal energy of the electron, where K is the Boltzmann constant and T is the Kelvin temperature. Therefore, this charging energy should be greater than KBT. How much greater? Say approximately 10 times this KBT value. If that is the case, then Coulomb blockade will happen. No electron can tunnel from the source to the quantum dot. Therefore, this is called it as the Coulomb blockade. If EC is greater than 10 kBt, then the quantum dot blocks further movement of electron from the source. This you call it as the Coulomb blockade. Now we move on to single electron transistor. We know that today's microchip have billions of transistors, and in 1970 each transistor required say 10 million electrons, but today each transistor requires only 10,000 electrons, which means that the microchips are in nano dimension nowadays. Therefore the size has greatly reduced and the number of transistors has increased, and similarly the number of electrons in each transistor has decreased, and this paved the way for a single electron transistor. All these historical data is available from the Moore's law or Moore's plot. One can browse and see Moore's law, how the requirement of transistor will increase in the coming years from 1970. Right? So this plot can be viewed, can be browsed and viewed for further reference. But what a single electron transistor is that we want to transfer one by one electron from the source to the drain through the quantum dot. So that you call it as the single electron transistors. Requirement of transistors have increased, whereas the achievement of transistor action with lesser number of electrons, that paved the way for the single electron transistor. Here you have a schematic diagram of a single electron transistor. Here you have a source, here you have a quantum dot and a drain. So quantum dot is going to act as a gate. So when you bias source and the drain, the electron cannot tunnel through these insulating layers to the quantum dot because of Coulomb blockade. We have to bias this gate so that the Coulomb blockade can be overcome, so that electron tunnels from the source to the drain. Let's see how. Here we remember that this is the EC value, charging energy. If I want to add an electron to the quantum dot, the energy, charging energy is given by EC. EC is equal to E square by 2C dot. As the capacitance is very less, I have to supply greater energy. Right? We also know that EC can be written like this, E into V, where E is the charge of an electron and V is the potential applied between the source and the drain, and which can be rewritten like this, V is equal to E divided by small e, charge of an electron. And if you substitute this value here and simplify, you get E divided by 2C dot, or E power 1, which is nothing but E divided by 2C dot, as this denominator E cancels with this E square 1E in the numerator, and we get E by 2C dot. Now this much voltage has to be supplied to the gate in order to overcome the Coulomb blockade, and this you call it as the gate voltage, Vg, which is denoted as Vg. And now let us go through the working of a set as indicated in the schematic diagram. Here you have a source, thin insulator, quantum dot, thin insulator and a drain. If you bias, if there is no bias, then nothing will happen. Here in the band diagram it is very clear that the energy levels of the source and the drain remain at the same, whereas due to Coulomb blockade, the energy levels of the quantum dot will be shoots up. As a result, no electron can tunnel from the source to the quantum dot. And what happens if I bias this source and drain? So this is indicated in the diagram. The energy level of the source increases, the energy level of the drain decreases, but still the quantum dot the Coulomb blockade in the quantum dot prevents tunneling of electron from the source. So in order to overcome this, now I bias this quantum dot with a gate voltage, say Vg, which is given by E by 2C dot as shown in the previous slide. Now what happens? The energy level of the drain, the energy level of the source shoots up, the energy level of the quantum dot decreases, that is, Coulomb blockade is overcome, and the energy level of the drain is further lessened. As a result, the electron from the source tunnels into the quantum dot, and as one extra excess electron is available now the energy level will go up, therefore second electron cannot tunnel through. Then the electron which has occupied the quantum dot from the source will tunnel through the insulating layer to the drain, so that now the energy value will increase and the second electron is ready for transfer. So a single electron, one by one electron, can tunnel from the source to the quantum dot and from the quantum dot to the drain. So this you call it as the single electron transistor. At a time, only single electron can tunnel through the insulating barrier from the source to the quantum dot and from the quantum dot to the drain. So this phenomenon you call it as the single electron transistor phenomenon. Thank you.